Okay, welcome in everybody to session number 6 of LLM Engineering, Cohort 3. Today we talk pre-training, and this is going to be a big session because it's going to all come together today. I'm really excited to kind of walk you guys through everything we've learned so far and bring us all the way up to the point where we're going to be able to really start building, shipping, and sharing some awesome LLMs that hopefully you guys will use for some production LLM applications. I've seen just a few folks sharing this week. So again, Nalay, all over it. Love to see it. I also wanted to encourage all of you to give the additional thing that I was sharing a little read in the Discord, because you guys are exactly the kind of people I'd love to get your opinion. We're working on a brand new course, and it's just an email course that we're going to offer for free that tries to get people up to speed quicker on the concepts we've covered in here. So if it doesn't make sense to you guys, it's probably not going to make sense to anybody. I'm trying to live that build, ship, share ethos. And so feel free to jump in and tell me what's terrible about it, and I will fix it. If you guys want to get some accountability next week, get started early in the week, first thing on Monday. Join us. These accountability sessions are getting bigger and bigger, and they're only going to get bigger with cohort launches coming in the next few months. So really excited about the way those are going. If you're looking for some accountability, there's a nice little crew of accountability that really I'm seeing a lot of posts go out, and there's a lot of energy around the first of the year. So start getting after it before it's Jan 1. Next week, we're covering VLLM. So that's what we're building, shipping, and sharing. Put it on your calendar if that's of interest to you. All right, so with that, let's get into it. Let's align our aim to the day. Again, we are through module 1, and we are now into module 2. This is a big deal because now we can really start to understand what's going on with this meme. Now we can really start to build some LLMs. But there's some details before we get out of the weeds that we need to go down and figure out. We need to understand loss today. We need to understand how it's connected to training models. We need to understand how what we might have heard about, what we might have learned when training a simple machine learning classifier is actually kind of right at the heart of training these more complex LLMs. And we start to get some intuition and some inkling, some foreshadowing into things that we're going to see when we meet alignment techniques like reinforcement learning with human feedback. And all of this is kind of quite related if you look at a deep enough level. That's exactly what we're going to do today. We're going to talk about how training is kind of the entire space that we're going to look at over the next half of the course. And there's a lot of specific words that we're going to learn to navigate: unsupervised pre-training, supervised fine-tuning, and we're going to start really getting our feet set on the ground with that. We're going to train nanoGPT from scratch today. And finally, we're going to actually import Llama 3.1, the model that you should be using at your company today if you're going to be looking to use open source models off the shelf. So we like to say everything is loss. You might say everything is pre-training, everything is training. Once you can kind of say that and feel that and see that, then you're exactly in the space you need to be to really, really be able to start teaching others about what matters and what doesn't. Okay, so let's get into it today. Let's talk about loss. When we talk about loss functions, we need to understand that, first of all, to train a model, we must know loss. Okay, cool. Now, you guys already know loss. Loss is something that we've all learned a long time ago in math class, or we learned when we first started studying machine learning. You can do loss on anything. The loss is like the error. You remember y equals mx plus b, root mean square error? You remember that? It's the same kind of idea here. What's the difference between actual and predicted values? We've got a few definitions here. And these shouldn't feel foreign to you if you've done any work at all in math. Loss is just this difference between the actual and the predicted value. It's what is lost in prediction. It's the prediction error. That's it. And so if we look at what a loss function is, classic Andrew, it's the difference between the actual and predicted across a whole data set. And, there's lots of ways that you've probably seen this visualized before. There's lots of, mathy looking ways to talk about these equations. And, the intuition is what matters here. This is all there is to loss functions in general, mathematically. We want to use this for LLMs, though. How do we use loss when we train LLMs? Well, what we do is we first measure our distribution of potential next tokens. And then we say, well, we actually want to move this distribution a little bit closer to the distribution that we want. We want to kind of take what we have and move it closer to what we want. That's it. And that's really what we're doing when we're training any model, including LLMs. So how do we calculate this loss? Well, we actually calculate it the same way we do in a simple classification problem. We use something called cross-entropy loss. Now, that's the same theoretically. It's not the same necessarily in practice, in code, because the setup is just a little bit different. But it's not that much different, as you'll see if you go back and you sort of look at classical machine learning with fresh eyes. Cross entropy. What are we looking across exactly? Between what two things? Well, we're looking across the logits and our targets, basically the training data, the correct next token, right? We already know about logits. And we can think about this. This is the same thing that we're doing when we're doing fine tuning, by the way, as we'll talk about next time. But we've got some sort of generated distribution and we've got some desired distribution. And we want to kind of merge these things closer together. We want to make sure that as we're looking across generated and desired, in our context, these are called logits and targets, that we're trying to really match what we know we want, the next token that is going to be predicted. Here's some little Shakespeare action. Spur me, have I done? Name that Shakespeare play. And we want to kind of get these things to agree on the next token. I mean, that's when we know we're going to kind of have trained it well enough, right? And you might say, well, like, what's well enough? It's like, well, I mean, you're probably hearing a lot about how you can keep adding more data and keep training longer for all different types of sequences. And the other thing we can take a look at here with a diagram like this is we can think about this little bracket. This little bracket here, you see the words moving through it? That's the context window right there. So we're literally sort of moving the context window as we go because the context window is a fixed size. Now, we're going to talk more about doing things in context a lot, but it's very interesting to think about training versus inference. And we really, really want to be firmly in the training category today and in the next few classes. So keep this in mind. We know the answer when we're training, okay? It's important. Let's think about and review logits. LLMs, they pick the most likely next token. We've covered this. Well, that is done, as we know, through the decoding process. This is after we've moved through our decoder block. How is it done exactly? Well, we take the soft maximum of all of our logits, and then we do what? Well, we sample that distribution that's created. This softmax we've seen visualized here. And it's, again, it's the softmax of the logits. All right. We're just going to keep beating this to death here. What's the logits? Well, those are the specific scores of length vocab that are going to give us some information that we can use to select the next token. Let's just zoom way in on this for a second. Let's define logits. They are the raw, unnormalized scores for each token in the vocabulary. Remember, it's already been projected up from the linear projection layer. And then we take the softmax to get now from an unnormalized raw score space to a normalized probability space for each token. Now we can say we're indicating the likelihood, we're indicating the probability, we're indicating the odds of selecting this next token. Okay, so we've got some vocabulary we've just covered: loss, loss function, logits, softmax. We're still not quite there with cross-entropy. And what are these targets exactly? Well, cross-entropy loss is rooted in the same kind of place as what we've studied so far, right? So the logit is the logistic unit. It's the log of the odds. Well, cross-entropy loss is also known as log loss. So what's the entropy then exactly? Well, the entropy here is really kind of the amount of surprise that's in our next token prediction. Remember, we talked about if we're 100% sure, then we'll definitely predict kind of a boring token. So we kind of can intuit our way pretty far by kind of realizing that cross-entropy loss is also known as log loss. And we use the logits, which is just the log of the odds. So let's go deeper into this idea of entropy. This is something that is like from Claude Shannon way back in the day. I just want to note here that these two equations are equivalent because of the rule of logarithms. And that is kind of something that after you go through the lecture, the code today, you can go back and you can really start to play with some of this stuff. It'll kind of bring you back to math class. We're not going to derive things by hand in here. This is about developing really strong intuition. So whether you use this form or this form, entropy is trying to kind of quantitatively, I should say, assess the surprise. Okay, so this is a great example from an absolute legend. Speaking of BAM and triple BAM on YouTube. And this is like, how surprised would you be if you had 6 orange chickens and 1 blue chicken if you selected an orange chicken? How surprised would you be if you selected a blue chicken? And you can see sort of, you can go through a calculation here and you can get the entropy associated with kind of the probability of selecting a orange chicken. Okay, so how surprised would you be? Now, this idea of entropy, we got to kind of expand it a little bit, because this is a little bit more ground level than what we need. We need cross entropy. But when we see entropy, it kind of reminds us of what we studied last time. It kind of reminds us of the odds. that we took the log of, and that's how we got our Logits. And we can kind of put these things next to each other, and we can kind of imagine them playing well together, let's say. And indeed, they do play well together. Now, we're not calculating just entropy, and we're not calculating just Logits. We're calculating the loss between or across the generated Logits and the predicted values. And so like that's kind of not exactly perfect language for LLMs. Rather, what we can really zero in on is if we say, well, generated, those are the Logits, predicted, those are the targets. We can kind of use this now to develop some sort of single number. This is a key that we can then use to try to optimize everything else in our system towards. This is fundamental for any type of training or fine-tuning or alignment or optimization in general. So these Logits, we've seen them before. We've visualized them before. And these targets, these are just the words that we know go next, because we're training. We're not doing masked stuff here like we are when we're doing inference. We want to know what the answer is. And so if you look deep inside the code here, it's really interesting, because if the targets exist, if we know the answers, then we can calculate the loss by taking literally just boom, cross entropy, as Wiz always says. The code's actually pretty easy. Logits and the targets. Meanwhile, if we're not doing training, that is, if we don't have targets, that means we're doing inference. And then we only need the Logits because we don't want the answer, because we want to predict the next token. And, you know, this kind of use of these Logits in training and in inference is really at the core of what we want to understand. And yet there's just a little bit more here, because what we're going to see is that there's actually loss functions at the center of like everything that's happening these days. So let me give you an example. Cross entropy is actually just this entropy plus a relative entropy. And you can imagine how the math works out to get us a multiplication out of an addition here with logarithms. Well, it turns out you can rewrite this equation for relative entropy. And when you do, you actually can change the name of relative entropy. And you can change it to something called KL divergence, Kubler-Leibler or something like that. Couple of guys, KL divergence. And this is really an important idea because we use it. And we're going to use it 2 sessions from now when we cover reinforcement learning with human feedback. It actually helps make sure that things aren't too far apart, right? Which is exactly what we want to do when we're studying loss. Okay, so if we think about kind of where you need to be, like coming into an interview here, you need to be able to crush what is a loss function. You need to be able to crush what is cross entropy loss, Logits, targets, and you need to be able to sort of understand the difference between training and inference here. You won't need to be able to derive anything on the whiteboard. Now, just a little bit more here, and just recall as we set up our build for the day, stuff we've already talked about since session 1. We talked about how the GPT style transformer is the decoder only style. We talked about how it doesn't have that encoder. at all. We looked at how nanoGPT is what we're actually using today. And it doesn't have one decoder block, but it has 1, 2, 3 decoder blocks. We talked during session 1 about this idea of pre-training. We briefly touched on it. And we said pre-training is like this giant Shoggoth, this giant, crazy, evil monster, but also that has the capacity for great, amazing things, that is trained on all this internet data, and we're not really sure what it's going to do, and takes all this money and GPUs. Nobody can create a business that actually works based on training these things these days. Like this is a beast to deal with. And then we also talked about how there's all this other post-training stuff. And we alluded to some of this RLHF and some of the stuff that we'll dig into in future events. Now, it's important to understand all LLMs and SLMs today, small language models today, they really are GPT-style transformers. And when we talk about training or tuning or alignment, we're really talking about this process of taking the logits, taking the targets, and trying to get them closer. So really, everything is kind of loss. And we're going to see this in practice today. We're going to see this with nanoGPT, model that we've already gotten a little bit comfortable with. Easy, simple, small. It's kind of mimicking GPT-2, which we'll talk about. And then, of course, from Andrej Karpathy. And, you know, he said we should train a character level GPT on the works of Shakespeare. So let's see what we'll do today. We're going to do some simple training. We're going to get the dependencies. We're going to train this Shoggoth today. We're going to do data prep, and we're going to build a training loop. And knowing everything that you know now, I'm pretty sure you understand a whole heck of a lot of it. Wiz, let's see how to do this thing from the ground up.
Oh, yeah. Okay, so this is what we've been working toward the whole time. Training big model. We're gonna train a small model today. But you know, this process scales up. That was the findings of the paper. So we're gonna go through and talk through this. Martin, I'm gonna answer your question as we move through the material. So, okay, the loss function in LLMs, right? So first of all, let's just grab some dependencies. Not a big deal. You know, we'll download nanoGPT again, and then we'll prep our data. The first activity you guys have to do is look through this data prep helper function, figure out what's happening, right? So what's going on in here? It's not too complex, right? There's only 32 lines of code, a few of which are comments, but it's pretty important what happens. When we go to the loss function here, we have the question, we have the training loop. The question is easy. Just talking about tokenization. The training loop is not as easy. So there's a lot of code here. Tons of code, in fact. So we're going to work through it, you know, at a decent rate. We're mostly just going to pay attention to some things that we already know. So when we look at, say, for instance, the, you know, in this case, let's talk about the, you know, what we know, which is that encoder decoder style. We have a number of kind of blocks that we're used to, which is like 6 blocks of you know, the encoder, 6 blocks of the decoder. The difference between what we're doing with this particular model, right, is we're just using that decoder stack by itself. So we don't actually have an encoder stack. this is just something that works out, to be clear. It works because the volume of data we use is much higher, and because we use a ton of decoders in a row. So we are essentially training the model to just be good at the decoding part of the process, which is predicting the next token as we've defined it. So the idea that we need to encode something is not literally true here, right? Now you might say to yourself, well, but hang on a second. Doesn't the model have to have some kind of encoded representation of text? The answer is yes. That's done through embeddings. So Martin's question, are embeddings outputs from the first two coder blocks or logits? Embeddings are so there's a couple questions there, a couple of things that we should talk about, right? Which is that you know, the output of the decoder stack or blocks is absolutely just still dim model. So this is our information that we have in front of us here on the screen, right? So our n embed in this case, that's still true. So they're the same dimensionality between our embedding space and the actual way we're processing information through our model. Secondly, the output or the logits are actually, huge, right? Because it's got to be the whole vocab. But the thing is, we need that internal representation. That's what we pass around inside the model, including from the decoder stack to potentially an encoder stack, or from encoder stack to decoder stack, depending on the architecture. In this case, from decoder stack to decoder stack. The dimensionality remains pretty much the same, pretty much locked in the whole time. We are adding information to those vectors as we flow through the information. There you go. Okay, so for learning rate, we're just using a small learning rate here. Classic. We're going to decay it. We got some beta parameters. We're not going to worry about all this. We're going to talk much more about these things later on. But for the stuff that we know, we have the kind of loading up some data, right? We have our loading up of model checkpoints, depending on if we're initializing from scratch or if we're resuming from a checkpoint. And then we have our optimizer. Our optimizer is just going to be pre-configured like we used in previous versions of this model. And then we're going to have the estimate loss. We're going to estimate our loss because we're going to do this in a big batch process. Estimating our loss is going to be much more efficient than calculating it exactly. This whole thing of arbitrarily accurate loss means that we can get as accurate as possible. But again, we really just want to save time, and that's why we use this estimation. And then we have our learning rate decay scheduler. We haven't talked a lot about learning rate, but the idea of learning rate, and we're going to spend more time in this when we get to RLHF especially, is that if we think about learning rate, right? If we think about our loss function, and then we think about our loss landscape, right? So what does loss look like when we're training a model, right? If it's a function, then we can probably visualize that it's got some slopes, and we visualize it in this classic 3D, space where it is like a landscape, like mountainous terrain. Then our learning rate is kind of how far do we step, right? Every time we do another iteration, are we taking really big steps? Are we taking smaller steps? And that's what that scheduler does, is it changes, if we're taking these really big steps or we want to take some smaller steps. And you think of it this way, right? If I have a big old valley, right, and I want to get to the bottom of the valley, if I take a really big step, I might step over the valley, right? Miss it entirely. If I take very small steps, it's going to take me absolutely forever to get to the bottom of the valley. The learning rate scheduler says, let's take some bigger steps until we get to the point where we can, we're more confident, then we're going to take some smaller steps. All of this is, we're going to spend a lot of time on each of these in specific as we go through the rest of our time together when we talk about fine tuning, but it's very important in training, right? So the initial pre-training is where we're going to be we need to learn a huge volume of information very quickly, and then we're going to slowly learn more and more, right? So we're going to understand some basics of language very quickly, and then we're going to slowly expand. And the way that we do this is through this learning rate decay scheduler. Okay, so that our model, right? We've talked about what it looks like, and this is what it actually looks like. So not just 3, but 12 blocks of decoder in a row, over and over again. Decoder, 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 right? You can see that we have our word token embeddings, and we have our positional embeddings. We have some dropout, classic, right? You'll notice that we have this output dimension of 768 for both. And our linear layers, or our the internal dimension of our model, is also the 768. Again, to Martin's question, where these dimensions are similar, and only when we get to the final linear projection layer do we go back up to that 50,000 tokens, right, which is our vocab. So what we've essentially done is said, remember how we had 6 and 6, you know, encoder, decoder? What if we just had 12 decoder? And it turns out it works great. All of these layers should be familiar to you guys. The only kind of like catch is that they're using a slightly different activation function. We're not going to go into it. It just works very slightly better. And then that's it. Okay, so there's a discussion question, which is, how is this different from the transformers we've seen so far? It's still a transformer, right? But there's something distinctly different about it. We've talked about it a bunch of times, but you know, have a discussion and really try to pick out where does this differ. Okay, so now we are starting to approach getting to training. Okay, so training. The first thing we need is some data, and we need 2 different pieces of data, right? We need some inputs, we need some outputs. As in, we need some, input to our model, and then we need some kind of thing that says if we were correct or incorrect when we generate the next token. Now, this is true. This is still how we pre-train today, okay? Despite how simple this is. In order to get labels for every token in our data set, with the exception of technically 1 token, right? We simply offset the sequence by 1, right? So our X, which is our input here, our features, right, has the sequence 18,000, 11, 350, 460, 21,000. And then our Y, or our target, or our label, right, is just 11, 350, 465. You'll notice, right, the label for our token is just the next token that should come in the sequence. That's it. And that's how LLMs happen, right? So we just get really, really good at parsing through billions and trillions of tokens of text in order to be able to just get really good at predicting what comes next. So that's it for our entire, setting up our entire training, right? We just have, the label is just the next token, which brings us straight back to what Greg was talking about with our loss. We'll get to in a second. Okay, so now we have our training loop that we're going to construct. So we actually have to train this model, and it's pretty straightforward. We get our learning rate from our scheduler, and then we update some parameters, and then depending on whether or not this is an evaluation iteration or not, we're going to do some evaluation. Otherwise, we're going to do these little steps. Don't worry too much about micro steps. The way to think about this is we can technically do a bunch of steps in a row and then accumulate the total loss, as opposed to needing to get the loss for each step. It just makes it slightly more computationally efficient. But all we do, right, is we get some logits and some loss from our model. That's it, right? And then we use that loss, we scale it by the gradient accumulation steps, don't worry too much about that, and then we do our backward pass based on what our loss is. And that's it. That's all of training, right? We take our model, we get it to do this prediction, we determine the logits or the raw unnormalized scores and the loss. Then we use the loss to do an update. Once we do the update, we rinse and repeat. And we do this a lot of times in a row, right? With a ton of data. But that's all we're doing. That's it. And I want to spend 2 seconds just discussing two important things, right? So one thing, we talked about our cross-entropy loss. We kept talking about how we feed it logits. So I'm going to tell you guys a secret. The first thing that happens when we pass the logits to our cross-entropy loss is we apply softmax. So, because remember what Greg said, what we're doing is we're looking at distributions, right? Logits are not a distribution. I mean, technically you can call anything in a sequence a distribution, but it's not a probability distribution, which we need for cross-entropy, right? So what we do is we take those logits and we just calculate softmax. Now you might say to yourself, well, why not do it ahead of time, right? Clever computing means that we can actually do the softmax at the same time as we compute our cross-entropy loss. So it's more efficient to have that softmax operation in the loss function so we can combine some calculations together. But the idea is, right, that we take this distribution that we've produced, that our model has produced, which we can calculate or compute from those logits, and then we compare it to the distribution it's supposed to be, which again is just this. It's just the sequence shifted ahead by one token, right? So that's what we do, and we try to get as close to that as we can with every prediction. We try to get as close as we can, right? And yes, it is softmax all the way down because in order to compare two probability distributions, they must both be probability distributions. But clever computing means it's more efficient to do this step outside. So this training will occur. There's going to be loads of steps. Lots of scrolling. But the idea is that you're going to be able to see at each section what's happening and how we're computing loss and how we're computing logits, right? So we have, not a word of joy, some comfort, nurse. And then we have a word of joy, some comfort, nurse. So this idea that we have, we can see exactly the sequences that are being trained as it's being trained. You'll also notice that we are working with the raw tokerinos here. So these are the tokens. So we're not, actually using the words. We've just built in a helper function in our training loop that lets us see what those words are by decoding the tokens. But that's it, right? So all we do is we make a prediction. We get a softmax distribution efficiently through cross-entropy loss, and we compare our distribution to what it should be, and then we update in a way such that we try to get that to be smaller. And that's all we do for millions of operations, billions of calculations, right? And eventually the thing can produce Shakespeare. And that's it. There you go. Okay, so in the notebook, you're going to walk through this. There's a couple questions, an activity. The big thing to understand is this core training loop, which again, just comes down to this kind of like section here. Though please through the rest of it. That'd be great. Okay, with that, we'll go back to Greg and get us into our first breakout room.
All right, let's go. Breakout room time, everybody. So let's take a look at nanoGPT together, how to train it. And we got 12 decoder blocks here, you said, Wiz, right? Not 3 as in the visualization. Okay, so we got 12 of these bad boys. Spend some time together on this training, and then we're going to come back and we're going to connect some more dots to really, really make sure we understand what the story is about how all this came about in the first place. Enjoy the code, enjoy the conversations. We'll see you guys back in 20 minutes. Okay, and we're back from the break, and it's time to put everything a little bit more in context. Okay, so unsupervised pre-training is what we talked about today. And you may recall that we started to tell you a little bit about GPT in session 1. GPT came out in June 11th, 2018. And the main finding was that pairing supervised learning with unsupervised pre-training, dope. And they had this main chart, and the main chart kind of took 4 different data sets, 4 different tasks. And over here on the left, they did some unsupervised pre-training. And over here on the right, the dotted lines are just fine-tuning. They kind of piddle along. Some of them do okay. And then these lines are supervised fine-tuning after unsupervised pre-training. And you kind of get this nice result with very little fine-tuning after you do all this kind of unsupervised pre-training, loss function decreasing hard work. And so really, the training process now has become the de facto standard of doing this unsupervised pre-training. First, this is huge data, all the data. We want general intelligence here. And then the supervised fine-tuning is more about, let's get better at specific things. Let's lift the distribution and our performance in that area up here and here and here. And there's some sort of general ways to do this that we'll talk about as well next time. And we'll get some intuition on when we do our second breakout room today. But let's go deeper into GPT. Now, we covered the transformer. When GPT was released, they said, we're improving language understanding with unsupervised learning. Now, where did that come from? Well, it came from, yes, the transformer. But where did the transformer come from? We're going to look at a couple of things. One of the earliest pieces of work that OpenAI did was the unsupervised sentiment neuron. And this was something that got pretty good at sentiment analysis from doing just unsupervised learning. Turns out just assessing sentiment is not that difficult of a task. And we can kind of see that even from this chart. The purple line here is the sentiment neuron. This is the one that kind of gave them the insight into maybe this could work for all of the other things. And this is one of the early pieces of research circa 2017 after the transformer came out. And of course, it even gets better after you do a little fine tuning. Now, we're not going to go too deep into the unsupervised sentiment neuron because it's pretty straightforward. You use unsupervised learning and then you're off. The two pieces that are particularly important for us, the first and most important is the semi-supervised sequence learning. This kind of was really, really foundational, a nice little leap forward that kind of led to the transformer, as we'll see. The other one was called universal language model fine-tuning. Universal fine-tuning. Makes intuitive sense already. Let's dig into semi-supervised sequence learning for a minute. What they did in this paper, and this is from 2015, they said, well, we're going to look at two approaches. We're going to look at the approach of predicting what comes next in a sequence. This was a classic NLP kind of task. And then we're going to also introduce this idea of a sequence autoencoder, where we read an input sequence into a vector, an encoded or an embedded representation, and we predict the same sequence. Let's take a look at the abstract. The abstract kind of says, hey, we got these two approaches, and we think we can improve RNNs with them. We're going to predict what comes next, and we're going to have a sequence autoencoder. These two algorithms can be used as a, quote, pre-training step for a later supervised sequence learning algorithm. Awesome. Here we see and we meet our good friend pre-train. Turns out using both of these, we can get more stable and more better with our models. Fantastic. Let's visualize what this looks like. This is the autoencoder that simply reconstructs the sequence. What is it doing? Well, it's taking a sequence, W, X, Y, Z. It's reading that input sequence into a hidden state, right? The hidden layer in a feed-forward neural network, for instance. And that's the embedding representation that we're reading it into. We're going into embedding space. And then we're using that understanding of the input sequence to reconstruct the original sequence. If we kind of highlight a few things here, we can see how the reconstruction is happening. based on reading in the input sequence. Very cool. And kind of giving some familiar vibes. This idea of an autoencoder is just something that learns efficient representations. You might call these unsupervised encodings, or today we might call them embeddings. This is just transforming the input data. And then there's this process that, oh yeah, of course, it's the decoding process where we're recreating the input data from our encoded representation. Now, typically this idea of an autoencoder had been used in kind of this PCA, T-SNE dimensionality reduction space prior to this, the unsupervised learning space. But here we're kind of doing this semi-supervised sequence learning. It's semi-supervised and it's using this autoencoder. Auto meaning we don't really need labels here. We kind of generate them automatically from the data that we put in the input sequence. And so we can learn the embedding representations. We can use the embedding representations to decode. And so the autoencoder is actually doing encoding and decoding, which sounds and looks quite familiar to us now at this point. And in fact, naturally, the transformer, of course, would follow from something like this. Now, you may remember also there's another piece to this puzzle that it used to be that people said transfer learning a lot. This is a term that has kind of died, and it was a big deal when we talked about pre-trained models all the time. Now we assume they're pre-trained, and we've kind of dropped that. Pre-trained has given way to pre-training, which we say a lot. But this idea of applying transfer learning in general is the idea behind universal language model fine-tuning. Now, this was focused on a number of different text classification tasks, but really they were like, hey, we can use this single dope model for all these different tasks. Isn't that cool? And prior to this, they were like, really, we need a lot of task-specific mods and training. We propose not doing that anymore. We propose doing a pre-training step. Here we are. And then a fine-tuning step. Beautiful. Okay. Absolutely lovely. And of course, the rest is history, you might say. GPT came out and they did 12 blocks. They trained this thing on 512 token sequences. Weird. And they used just a little bit of data. They trained it on some well-known data sets at the time, including Books Corpus and including Common Crawl. And we'll get into the data more next time. But they trained it on a number of different tasks. And one of the keys that is important for you guys to kind of focus in on now is knowing what we know, we can actually kind of think about how we got to do the input. We've got the 12 blocks, and then we might put a slightly different head on the top. We might sort of decode in a different way to do a specific type of task. And these are kind of looking at the different tasks that we might do, input and output and head we have on it. And it turned out this was really good at a number of different tasks, as ULM Fit had kind of shown we could do, and of course, as the autoencoder that we saw in semi-supervised sequence learning could do quite well. This was, of course, 2018, after Attention Is All You Need came out, and they were leveraging not the encoder-decoder stack, but the decoder-only stack. And it still worked. They were like, this is wild that this works there's still kind of this very brittle generalization. It needs a lot of compute. We think that there's like a lot of problems here, a lot of challenges, but it like works really well. And we think that it learns to perform many of the tasks that we evaluated on through this sort of attention mechanism. And this kind of transformer helps with this transfer learning idea. And well, indeed, it did help with the transfer learning idea, as we'll see as we continue our story next time into GPT-2 and beyond, as we go deeper into this fine-tuning paradigm. For today, this has all brought us to this big moment where we finally get to do the things that people using these tools in 2024 and in 2025 will do. Welcome to Hugging Face Transformers Library, aptly named. Now, you won't be surprised to see that it has PyTorch under the hood. It's abstracted us away from that. Transformers provides APIs and tools to easily download and train state-of-the-art pre-trained models to save you the time and resources that would be required to pre-train, to post-train, to train models from scratch. Wiz, is this really the way people are doing this today in real life, in enterprises? They're importing the Transformers library? This is sort of like, this isn't just like an academic thing.
There is certainly other tools that exist. There are certainly use cases for which people are using more specialized libraries, or perhaps even needing to write the PyTorch implementations themselves. There are a number of suitable alternatives for industry. That's all to say that yes, Hugging Faces Transformers is, I would say, the gold standard among these resources. Even in industry, especially in industry, right? Transformers is a tool that lets people work from all scales, right? From the kind of, mom and pop shop all the way up to people with millions of monthly active users. Yes, it's so ubiquitous in the industry that it's kind of insane. And there are very few tools that come close to it, except for hyper specialized use cases. I will say that there is one case where Transformers is probably not going to be the best tool, and that's if you're working at the largest possible scales of data. So something like the new supercluster that was built by Elon and friends. They're probably going to need something a little bit more custom than Transformers. Though I'm sure Transformers will have a PR to support it. As soon as they were able to, if they were made able to. So,
Okay. So Transformers, and then when we go into this pre-trained model library, one of the most popular models today, and what we recommend for our clients to start with if they're going to start experimenting with open source models, is the series of llama models from Meta, the large language model Meta AI llama, right? And these have actually become really, truly state-of-the-art. We'll cover how they get trained and all of the crazy fine-tuning and post-training. We'll talk about exactly how that all comes about. And we'll talk about what this dash instruct is doing next time. But this really is kind of the starter model that if you're going to start building, shipping, and sharing, you should kind of pull off the shelf, right?
yeah, I mean, the Llama series of models are the gold standard of open source models. It isn't close. There are a number of models that have more specific use cases that might be a little bit stronger on those specific use cases, but In terms of like a general model, this is fundamentally your option, as well as the fact that Meta continues to innovate and improve on these models, which is gives you that kind of forward-looking warm blanket. One thing to keep in mind as well is Meta through Llama has been doing this from the start, right? We'll remember back to the first kind of big open source model, Alpaca Llama, right? This first, foray into this weird world that we have where you can have a comparatively incredible thinking machine by going to Hugging Face and downloading some weights. One thing to keep in mind, right, is when we talk about these models, when we talk about how to get these models, you'll notice that we're getting them from the same place. Companies like Meta are trying to offer weights and be a weight repository, but like the first place that they're available is through Hugging Face checkpoints, and that's not an anomaly, and I think speaks volumes to just how pervasive that Hugging Face ecosystem is. That the first place these models are available and the first place companies want their model to be available is as a Hugging Face Transformers checkpoint.
That's right. That's right. And in fact, Llama 3, that's on this slide right here, this was April 18th, 2024. And today, actually, and this is part of the game with all you guys today, Llama 3.1, that's July 2024. And so, stay tuned. Of course, they came out with 3.2. That was a little bit different, but, this is a quickly evolving space, but really Meta and the Llama models have positioned themselves as really industry leaders in open source. And even today, even this week, even recently, I've noticed a lot of people starting to talk about moving away from training models and really just picking up a very, very large Meta type model, maybe from somebody else. A lot of people are training big models, and it's a very, very hard space to compete in. And probably the best case for your business is not to do this yourself, even though that's what we spent learning the last 6 sessions on. So, I think we're in a great place now to say, okay, all right, what happens when we want to pick something up off the shelf? Let's take a look and see, Wiz. When we pick it up off the shelf, what does it look like? It looks like a GPT. Wiz, show us exactly.
This is the moment we've been waiting for. This is where we go from, PyTorch and this very low level, world to Transformers library. This is we learned how to build the shovel, and now we get to learn how to dig. I think earlier Greg said we built the engine. Now we get to drive the car. This is the satisfying part, right? Okay, so first of all, this is just the most brief introduction to Transformers. Transformers has like about 1,000 different tutorials at this point. So please feel free to look into those if you want to go deeper on what the actual library is doing. We're going to go deep over the course of the next few weeks together. Okay, so this is now what we do. No more giant impart blobs from Python or PyTorch code. No more downloading a repo and then all this other stuff. We just pip install Transformers, and now we can start working with LLMs. You do have to make sure you're in a GPU-enabled environment because they still need GPUs to run, but we now get to zoom out a bit. We're also going to grab these 2 additional libraries that we're going to completely ignore. We'll get into them later on. Okay, first thing first, you have to get the model, and Meta is a real for serial business, so you must be granted access to the model, which means that you have to sign up. This process should be very quick, probably about 5 minutes. The idea is that we want you to do this because we're going to keep going back to Llama. We're going to keep going back to this Llama 3.1 model as we progress through our journey together. So please sign up for the model today. Your peer supporters will be able to point out a workaround if you're waiting too long for the access, but we really want to make sure we sign up today. Okay, then we have to pass in our API token. Because we have a we have to get access. We need a token. So you'll notice all I do is I go to my profile, and then I click on access tokens, and then I can click on this create new token, and I can create a read or write token, name it. There you go. Away we go. We can now put it into our notebook, and that's it. We just have to prove that we have access. So now we're going to load the model. The blurb has some extra text for you. That's it. Yeah, so great question from Nile. How do we sign up? You go to the model card. Link is provided in the notebook. And then there's going to be a big old blob you click on. It's going to look exactly like this, where you have to log in, and then you have to request access. It's automated process, should be no more than 5 minutes. Okay. So, what does all these words mean? Meta, we know that one. It's just a company. Llama, right, is a family of models of similar or same architectures. 3.1, this is the version. There is not compatibility of the weights between versions. So 8B, 3 versus 8B2, you can't just swap the weights. In the subversions you can, so 3.1, 3.2, that's fine. And then 8B, this is our size of our model. And you'll notice that B, capital B for billion, right? We were dealing with 100 and some odd 50 million parameter models, so 150 million, and instead we have, now 8 billion. So we've kind of taken a big step forward, both in the abstraction we're using and also in parameters, a few order of magnitudes higher now. We have to load this thing. Don't worry about it. In reduced precision, we're going to talk about exactly what that means, but basically the weights are very big and we need to load them less big. So how we load models from Hugging Face is we get the model ID, which you can find just by clicking this copy button on the actual name of the model, and then we're going to set that as our model ID. We have to set this config. This is just so it works in the notebook. You don't have to worry about that. We're going to get into the details of what's happening in that config later on. And then to load it, we use auto model for causal LM. So all that PyTorch is wrapped up in auto model for causal LM. Causal LM, right? This is our autoregressive model. LM, of course, just means language model. So we have our from pre-trained. This is indicating that this model has already been trained. We're going to pass in our ID. We're going to pass in our quantization config, and we're going to tell it to go on whichever device the accelerate library believes it should go on, which is just called auto. Then we can load the tokenizer. So every model has a tokenizer. There might be sets of models that share a tokenizer, like the Llama family of models, but each model, you do want to make sure you're using its tokenizer, right? Because that's going to be what makes the inputs and outputs make sense. If we use a different tokenizer, they're going to correspond to different words, and our output will be super gibberish, which is not ideal. Then we can look at the model. This is the big part, right? So this should look a little bit familiar, right? Because we saw it in the previous notebook. So this is the model we had from nanoGPT. You can see that there. And this is the model we have from our new transformers library. And you'll notice it's pretty much the same. The embeddings are a little bit bigger, right? And there's a few more tokens in the vocabulary. And there's a few more layers, right? Instead of having 12, we have 32 decoder blocks in our stack. But otherwise, it's like the same thing. We have attention. We have our multi-layer perceptron, aka our feed forward. We have our layer norms. You'll notice that we don't have dropout here. This is, again, something we discussed very briefly in the last session. Dropout is a computationally expensive regularization technique. We super undertrain all of our models, and we use tons of data, so we don't have to worry so much about regularization with these big models. And then we have our rotary embeddings. Rotary embeddings, going to sound similar if you remember rope, right? And then we have our final LM head, which is our linear projection layer. And you'll see here that our input features is the embedding or model dimension, and our output features is exactly the same as the embedding because it is our vocab size, right? So this is the idea. But it's the same thing under the hood, right? Like it's the same, it's just much bigger, and they're using slightly more, slightly newer versions of what we saw before. So a discussion for you guys is going to be what is different, how do they compare, and then we can do some inference, and inference is was a little bit harder with the previous versions of the model. In this one, we're just going to go ahead and get an encoded input, which is going to tokenize our prompt and return PyTorch tensors. We're going to cast those tensors to the GPU. Then we're going to send those tensors as input to our model. We're going to qualify with some generation config. So this is for our decoding step. We're only going to decode up to 256 tokens, and we are going to use sampling, so we're not doing any greedy decoding. And then we're also going to let our generator know what our padding token is, since we want to ignore padding tokens. And then once we have the token IDs from our model, we're going to convert those back to words and letters, and then we're going to return that to our user. And then so we ask the question, what is the meaning of life? We get, what is the meaning of life? It is a question that's puzzled philosophers, theologians, and everyday people for centuries. There's no one definitive answer, and on and on. You see a much more coherent response than our model that we trained previously had, due to the fact that this is 8 billion parameters. It doesn't say 42, unfortunately, but that's okay. We'll forgive it this time. That's it, right? That's all we needed to do is six lines of code to load up the whole 8 billion parameter model, and then run it, do some inference, and get it to answer your question as deep as what is the meaning of life with a almost acceptable answer. Okay, yes, bam, exactly. So with that, I'll pass you guys back to Greg, who can get us into breakout rooms.
Excellent. Okay, so this is where the rubber hits the road, everybody. I just want to point out one thing that you mentioned. Wiz, you mentioned auto model for causal LM with a causal language modeling head. You're talking about this language modeling head that we've been studying, right? This is the whole thing. The auto model for causal LM.
We called it the feed forward, or the linear projection layer, because that is what it is, right? But what it means is causal language modeling head. And this is this idea of a model head, right? If you're familiar with machine learning in general, is like we have a classification head for a model, right? This is the same thing, except our head is really good at figuring out what the next token should be.
That's right. Causal, meaning the last tokens cause the next tokens.
The old auto regression coming in, yes.
Oh, classic. Absolutely classic. All right, everybody, let's spend some time with transformers. So we wanted to end on a couple things. First, what kind of questions might you get asked? You might be asked in an interview, what model would you use? And the answer is llama. Okay, that's the answer. What you're not going to get asked is how would you use Hugging Face transformers? It's just not going to happen, because you use Hugging Face transformers. That's table stakes for any one of these jobs. They expect you to know how to do this already. So, just straight off the bat, just know, like, this is an industry standard. You're going to have to know it. We covered a lot of ground today, and we kind of tied a lot together. We saw cross-entropy loss. We talked about how entropy is embedded in this thing. So is the idea of the loss function. Looking across logits and targets is kind of fundamental to everything that we'll see next. We'll see fine-tuning, we'll see alignment, and this aligning of the logits and the targets, but secretly after the softmax. This is kind of the core of what we're doing when we're training, when we're pre-training, when we're post-training, when we're training it all. We'll see KL divergence later, put a pin in that. this idea of pre-training, we followed the thread, the golden thread from the autoencoder to the transformer to the universal language model fine-tuning, which is a great segue into fine-tuning next time. So we're going to pick up the story where we left off with GPT to talk GPT 2 and 3 next time. We saw transformers, auto model for causal LLM. You guys know now what that means. So few people really, really do. We're going to try our best to open up more time in the coming sessions for Q&A. Hope you guys enjoyed the additional discussion today. Please let us know what you thought about the session overall. How we can improve it is really important. So please leave some constructive feedback for us.